Hello, welcome to this new webinar on CivilFEM powered by Marc. Today we will be presenting the new features of the 2024 version. First, let's discuss what CivilFEM is. CivilFEM powered by Marc is a high-end general-purpose finite element software. Contains advanced analysis capabilities. It is suitable for all civil and structural sectors. It is developed based on Marc software, industry's leading nonlinear FEA solver technology provided by Hexagon. It has capabilities to elegantly simulate all kinds of nonlinearities, namely geometric material and boundary condition nonlinearity, including contact. Simplify and enhance management of civil engineering, structural, and geotechnical analysis. User can either use the graphical user interface or run Python scripts. Perform ultimate and serviceability limit state design according to steel and concrete international codes and standards. Pre-stressed concrete and advanced nonlinear simulations can be performed easily, including geotechnical tools, seepage structural coupled analysis, and thermal coupled analysis. Now, we will talk about the most relevant capabilities of the new 2024 version. New CivilFEM Soil Material. This material model incorporates two hardening mechanisms: volumetric hardening, which is governed by compressing state, and the shear mechanism that produces soil stiffness reduction, plastic strain, and dilatancy. Dummy shells for integrating stresses in thin structures, that is, one dimension smaller than the two others, modeled with 3D solid elements. Therefore, this capability allows modeling wall structures with solid elements that provide more accuracy and details, and to obtain forces and moments, results only available in shell element models. Structural elements can now be split into substructural elements. These substructural elements can be edited to modify their original properties. For example, you can assign different reinforcement areas to the same reinforced concrete slab. A reset displacement option has been added to load cases. This option simplifies the creation of initial state conditions for soils without self-weight deformation, or for obtaining only relative strains and deformations from the desired moment of the simulation. Cracking properties can be constant, temperature, and time-dependent, that is, concrete age, for early-age concrete cracking, to consider material softening, or cracking stress due to elevated temperatures. Warping degrees of freedom can be added to open steel sections. Additionally, rotational warping springs can now be included in the model. A new option to turn off dynamic effects in transient load cases. With this option, you can start your transient analysis from a steady loading state. The CivilFEM soil model is an advanced model for the simulation of soil behavior. As for the Mohr-Coulomb model, limiting states of stress are described by means of the friction angle, phi, the cohesion C, and the dilatancy angle, psi. However, soil stiffness is described much more accurately by using the triaxial stiffness, E50 modulus, and the triaxial unloading stiffness, E-ur. In contrast to the Mohr-Coulomb model, the CivilFEM soil model also accounts for stress dependency of stiffness moduli. This means that stiffness increase with pressure, hence E50 stiffness relate to a reference stress, usually taken as 100 kilopascals. The dependency of stiffness is calculated with the well-known formula extracted from the Plaxis hardening soil model. Also, when the material is subjected to deviatoric stress, the behavior of the model capture the hyperbolic relation commonly observed in drained triaxial test. An unloading-reloading modulus is included to capture the correct behavior in these situations. In the next CivilFEM model, we can see a simulation of a triaxial test made with the new CivilFEM soil model. We have defined the required properties, such as the second stiffness modulus value for a 50% of the maximum deviatoric stress at the reference pressure or the unloading-reloading modulus at the reference pressure. By default, the reference pressure is given as 100 kilopascals. We have defined 4 load cases. First, a confining pressure of 150 kilopascals is applied in the probe. Then, a loading phase is created to increase the deviatoric stress. Finally, an unloading and reloading phases are created to observe the behavior of this phenomenon and to reach almost the maximum deviatoric stress. For the post-processing results of this model, we can use the user result tool to create a result of the deviatoric stress by subtracting the minimum principal stress to the maximum principal stress. Then we can plot the deformation versus this result and check the CivilFEM material model results. We can observe that the maximum value of the deviatoric stress corresponds to the asymptote of the hyperbolic curve. Then we can see the second stiffness modulus for a 50% of the maximum deviatoric stress. This value will correspond with the one calculated from the reference value introduced by the user and taking into account the stress dependency, in this case 150 kilopascals. How do we go about code checking 3D models, especially very large models? How do we take data from 3D continuum elements and turn this into something the user can perform code checking on? Now the dummy shell capability can be used. For example, we have a 3D brick model and we want to do a code check evaluation. The mesh could be a tapered section, using even tetrahedron elements. Dummy shell capability converts 3D solid elements, assuming a laminar structure, into the forces and moments needed to evaluate a code or standard. With these forces and moments, then a rebar check verification or rebar design can be performed according to the code specification. The shell element model is created at that midplane. The thicknesses are pulled off from the global model, and then the results from the global analysis taking the actual stresses at the integration point through the actual 3D solid elements, and integrating those to create the equivalent shell response. The response will give the equivalent bending moments and shear force values both in plane and out of plane. Dummy shell tool is recommended to be performed on any 3D solid structural element assumed to have a laminar behavior. On this nuclear power plant containment building, the data from 3D solid elements of the wall and foundation are mapped into dummy shells. The 3D solid model is solved, including any nonlinearity as usual, and user can plot any result as stresses, displacements, and so on. Once the solid to shell conversion is performed in wall and foundation, then shell elements can be post-processed as usual. User can plot axial force, bending moments, shear forces, etc. Then user can carry out a code check, evaluation, or a rebar design according to any available standard. User can plot the designed area of steel for wall and slab foundation, or the interaction diagram of any dummy shell element. Shell structural elements can now be split into substructural elements. These substructural elements can be edited to modify their original properties. For instance, user can assign different reinforcement areas to the same reinforced concrete slab or wall. In this example, we have a single structural element, and we need to add new properties without creating new geometry nor new structural elements and without meshing again. There is a new tool in the shell structural element contextual menu to add or remove a sub-element. For example, user can add different reinforcement properties in finite elements of the same shell structural element. In this case, we will show you how to assign a different thickness in top elements. User can set a variable thickness, as you can see. User can remove the sub-element easily as well. A reset displacement option has been added to load cases. This option simplifies the creation of initial state conditions for soils without self-weight deformation, or for obtaining only relative strains and deformations from the desired moment of the simulation. The user just needs to activate the option at the beginning of current load case. The stress field maintains the previous values. Cracking properties for concrete can be constant, temperature and time dependent, that is, concrete age, for early age concrete cracking, to consider material softening, or cracking stress due to elevated temperatures. Both critical stress and softening modulus values may depend on age or temperature, and user can define tables for this dependency. Warping degrees of freedom can be added to open steel sections. This figure shows a simple fork-supported structural member which is loaded by a concentrated twist moment at the middle cross-section. If warping effects are not activated, then no warping normal stress will be computed. If warping effects checkbox is activated through the steel structural element, then warping normal stress in the middle cross-section is computed due to the concentrated twist moment. Additionally, warping springs can now be included in the model. You can simulate warping stiffeners by assigning the equivalent warping spring stiffness. This new checkbox indicates whether the selected load case in a transient analysis should use time integration, that is, whether it includes transient dynamic effects, for example, structural inertia, or whether it is a static or steady-state load case. At Ingesiber, we share our knowledge and experience through our training courses. Through the International CAE Education Center, where the courses are focused on the practical use of finite element software such as Patran, ANSYS MAPDL, or ANSYS Workbench. These are short courses lasting between 1 and 2 months, self-paced with interaction between students and instructors, providing continuous support and study materials in both PDF and audio-visual formats. There is complete flexibility to create any custom course for individuals or companies. Registration can be done at any time, and the course can start immediately. If, in addition to practical knowledge, a theoretical foundation in the finite element method is needed, there is an online master's program organized through UNED. It combines the fundamentals with practical use of ANSYS software, including Mechanical Workbench, MAPDL, SpaceClaim, Fluent, and ACP, that is, composites. This master's program has been offered for 30 years. The next course begins in 2025, and registration can be done in September 2024. You can contact us for more information about any of our courses. Thank you very much for your attention. You can follow us on social media and contact us via this email. See you at the next webinar.